Today we're going to take a look at section 11.2. We're going to look at curves, polygons, and symmetry, although I don't think we'll get to the symmetry today. So let's talk about what we mean by a curve first. A curve is an object similar to a line in a plane, and the easy way to think of this is a path drawn on paper. So just what you can draw with your pencil on paper. Curve does not mean it has to be curved, okay? A line is a curve. Okay, so don't think of it in terms of the descriptions we do. We had this discussion the other day. My daughter had on some gold-colored earrings, and my son was saying they're gold, and my daughter saying they are not gold. And so we had this discussion about the fact that I have a ring, and this ring is gold, but it's silver, right? That's what's going on with the word curve here, right? We have these sort of double meanings of the word curve. Here, curve means a path drawn. So it could be straight. Connected means a curve that can be drawn without lifting a pencil. No breaks in the graph or in the figure, whatever the shape is. That's connected. Simple means that the curve does not cross itself. And there's one more. I don't know why it's not on this sheet, but I'll go in the next one and then we'll come back to these images. The next one is closed. And closed means it's a curve that has the same starting and stopping point. So you can start somewhere, trace all the way around, and end up right back where you were at the very beginning without retracing any of your steps. Emily?
By simple, when it says like does not cross itself, does that mean like it can't like meet even?
No, it'll meet back up at itself,
Like, not intersect.
but it can't cross over itself. So like your image, yeah, I don't have this one down here. Your image, your classic example of something that would not be simple would be the figure 8. It crosses over itself in the middle, okay? And then a polygon, we'll do that one too since it's on this slide, is a simple closed curve whose sides are line segments and two sides of a polygon meet at a vertex. So fill those in and then I'll go back to my pictures from the first slide. All right, we have the blanks filled in for polygon. Okay, we'll come back to this slide in a minute, so there will be an opportunity again. All right, go ahead and draw these 4 figures on your paper if you would. And what we're going to do is we're going to label them in terms of their description. Are they connected, are they simple, and are they closed? That's our question for each of them. Okay, are they connected, are they simple, are they closed? So draw them first, and then we'll answer those questions second. Okay, the first one, is it connected? Connected means that there's no breaks in it. Yes, this one's connected, no problem on that. So this is connected. Is it simple? Simple means it doesn't cross over itself. Yes, it is simple. Is it closed? No, because it does not have the same starting and ending location. So this one is connected, simple, and not closed. Second one looks like a worm, doesn't it? Yeah. It's just the shape on the outside, none of the shape inside. It's not like solid figure filled in. Alyssa?
So all of these are curves?
These are all curves. Yes, they are. No matter whether they're curved in shape or whether they're straight in shape, these are all curves. Good question. All right, second figure. Is it connected? Yes, it is connected.
Generally, a curve could be just like a line on paper.
Yep.
Like, is there anything that cannot be a curve of a dot?
Well, it just has to be a path. So if you talked about a dot, that would be a curve just because it necessarily has width and so forth. But if you talked about a point, which has no width or anything to it, a point wouldn't be a curve.
Okay.
So,
But
yeah.
like a line or
Yeah.
anything.
Yeah. The second one, is it simple? Yes, it is. It is simple. And is it closed? Yes, it is. Same starting and ending location. How about the third one? Is it connected? Yes, it is. Is it simple? Yes, it is. Does not cross over itself. Is it closed? Yes. Starting and ending point are the same place. What our last one? Is it connected? Yes. So I don't actually have any pictures for you of something that's not connected. I'll draw one here in a second just for the sake of having done so. But how about simple? Not simple. Is it, what's my last one? Closed. Yes, it is closed. All right, so let's give another picture. All right, all of this being in a box, if you will, this would not be connected, right? Yeah, I have two separate shapes. And even if I did it like this, that would not be connected. If I have this, whatever it is, if I've got something where there's a break in the graph, you could even have something like this. If you remember from maybe an algebra course where you had a hole in a graph, that would not be connected, right? Because there's a break in the graph. Alyssa.
So with the two circles, it would be not connected. It'd be simple since they don't cross each other.
Correct.
But then unclosed, it wouldn't be.
Yeah, you can't be closed because you have two spots. Right. Exactly. So if a graph is not connected, it can't be closed, right? Because you can't start and stop somewhere without having to pick up your pencil and do that. Yep.
Like
Erica.
the two circles example, would that be one curve? Or?
Well, it depends on what you're describing it as. So they are each individually curves, but if you were looking at this whole shape itself, you could also call it, a single shape itself and call it a curve. It's just not connected. We don't see things that are not connected very often, especially not the graph of the circles like I drew, which feels a little bit funny, but yeah. All right, these are all shapes that are polygons, which is why I've got them all on this particular slide. So take a look at these. It says on here that a polygon is a simple closed curve. Okay, so it's connected, it's got the same starting and ending point, and it doesn't cross itself. But the sides are line segments. Okay, so now I can't have any curved sides, right? This is a curve, but none of the shapes have curvature on the sides. They're all flat because they're all line segments. And these are all different polygons because they all have these features, every single one of them. And they all have different names, and we're going to go through some of the names of these later. The names of polygons are dependent upon the sides, how many sides they have. Okay, so there are some different features about these graphs. The first one or these curves, the first one that we're going to talk about is there's one feature, there's one of these curves that is not like the others. Can you tell me which one is distinctly different maybe than the others? The second one. And the reason the second one is distinctly different is based on the next definition. So the next definition talks about something being convex. And I know you've heard that word before. You may not remember which one it is. But the two descriptions are convex and concave. Convex is a curve that is simple closed, and its interior contains any segment between 2 points on the curve. And then concave is a curve that's simple and closed, and it's not convex. It's one of those fantastic descriptions, right? And it's not the other thing. I love it when I ask my kids to describe something and they use the word in its own description. I'm sure you guys have never done that. Yeah, this almost feels like that, right? Almost feels the same as way. So we've got some shapes here, and we're going to talk about whether each shape is convex or concave. All of these shapes are simple and closed, right? Simple means they don't cross over themselves. Closed means they have the same starting and ending point. So we have those conditions met automatically. We're just deciding whether they are convex or concave. So let's start with the first one. What do you think the first one is? It's concave. And if we use the description that we're given for our vocabulary word, if you will, there, it means that I can take 2 points on the curve, and if I were to connect them with a line segment, I would have to go outside. Okay, let's use an actual line segment. There we go. I would have to go outside of the actual curve. I'm not inside the figure. I'm outside of it. And if I'm outside the figure, that is what it takes to make this a concave curve. Now, how about the second one then? Concave or convex? It's convex. And I can take any point on the convex shape, and if I connect them, I will be inside or in the interior of the shape. So I drew a couple of different ones in here. But it has to work for all of them, don't get me wrong. You have to be able to take any 2 points and do this, but in this shape we can do that. So that makes this, whoops, convex.
Well, from that definition, technically, why could you not just draw 2 points on the inside of the last shape?
Well, you can, but you can't do it for every 2 points, and that's the kicker. So Hannah's exactly right. I can take 2 points on our first shape, connect them with a line segment, and lie inside. That's totally fine. But I can't do it for every pair of points, and that's why it fails. Okay? How about our third one? Concave. Again, there are points that I can take over here on the sort of bottom side of this, that if I connect them, I'm outside of the figure, making this concave. And how about our last one? Convex. Same reason as the second diagram. Now, I realize that I did not read actually a part of our description. I read it, I think, but I didn't say anything about it, so I'm going to go back a slide for just a second. Any 2 sides of a polygon meet at what's called a vertex. So any of these sort of corners would be called a vertice or a vertex, okay? And there's several of them on all of our shapes. Those are called vertices, or singular is vertex. Okay, so I mentioned that polygons are classified according to their number of sides. So these are our 8 basic polygons. There's others, and we have other names for them, but these are the ones that, if you know these, then you're good to go. Everything else is one of those ones, you just go look it up on Google, because you know enough of them, so to speak. These are our 8 basic ones. So 3 edges, or vertices, it's called a triangle. 4 is a quadrilateral. 5 is a pentagon. 6 is a hexagon. 7 is one that you may not have remembered. It's heptagon. We don't see that one very often. 8 is an octagon. You see that one all the time on what? Stop signs. 9 is another one that we don't see very often. It's called a nonagon. And then 10 you see, you don't see it so much as you can draw it easily, I guess, as a decagon. Everything that's got deca at the beginning means 10, right? Decimal system, deci, deca, we get tens involved. Dodeca is 12, yes it is.
What did it say?
It's dodecagon, it's 12. Yeah, so these are our 8 most basic ones. And when we label polygons, oh, it's there at the bottom. They're named by their consecutive vertices in order. So they're vertices in order. I guess I actually sort of put 2 words in it that seem the same thing. Consecutive and in order mean the same thing. So if you go around, you got to go around the polygon in the same order. It doesn't necessarily matter whether you go clockwise or counterclockwise. But you can't, for instance, I'll take a shape over here. Let's say we choose this interesting concave figure right here. You can't go, let's call this A, B, C, and D. There's a vertex in the middle there too. This would be ABCD or DCBA, but you can't say DBAC. All right, so it has to actually go in some kind of an order, right or left, starting at any point around the shape. All right. A diagonal is any line of a polygon. That doesn't make any sense. What did I write over here? Does it say the exact same thing? Any line of a polygon of segment connecting that doesn't make any sense. This is the second time I've taught it, and it apparently didn't catch it the first time. Any line of a polygon, I think we just don't need the word segment. Connecting, there we go. Any line of a polygon connecting non-consecutive vertices of the polygon. That's what we want. So scratch out that piece right there. So if you take two consecutive vertices, it creates an edge. If you take two non-consecutive vertices, it creates a diagonal. So all I need is to take two non-consecutive vertices like B and D, and if I connect them, I will have a diagonal. And in this shape, it's quadrilateral because there's four sides. I end up with two diagonals, right? The one that comes straight down and the one that cuts across that are made to see. There's two diagonals for four sides. If I have one of these larger ones, like, let's see, over here on my second diagram, what shape is that? That is a decagon. And there's lots and lots of diagonals, right? So if I were to start working through with one, I have all of these diagonals here, and those are all the ones coming out of just that point right there, that one point. And then I'd have to go around this figure and do the same thing for all the other points. So there's lots and lots of diagonals for a decagon. Okay? All right, so let's talk about angles. An interior angle, or sometimes called just an angle, of a convex polygon determined by two sides having a common vertex. So this shape, what is this shape in here? Pentagon. Good job. It's got five sides. Pentagon. And all of the alpha with the subscripts, alpha 1, alpha 2, all the way up to alpha 5, are the interior angles. They're the ones that are not shaded in blue. They're kind of just clear or white or whatever. Okay? They're not colored in. An exterior angle is an angle of the polygon that is formed by one of the sides of the polygon and an extension of an adjacent side beyond the polygon. And the picture is just fine, but it sounds kind of weird when I state it. All it's saying is that this shape right here was your polygon. I'll mark it in, oops, hang on, let me try that again. I'll draw it in purple. This is our, in this case, our pentagon. It's not drawn perfectly, but you can pretend like it is. And if we extend one of the sides, like over here, then that side, along with the side that's already on the pentagon right here, would create an angle, and this angle, beta 1 right here, would be called an exterior angle. So you have to actually extend one of the sides. It's not that it goes between two sides all the way around. You extend one of the sides and you have the other portion of it. Now, we'll talk more about this later, but does anybody remember what would have to be true about an interior and exterior angle, like this pair right here? Good, they have to add up to 180. So we're going to see that information coming up later as well. All right, congruent segments are two segments of exactly the same length. So the word congruent right here has some sort of a resonation in our souls to the word equal, okay? But we don't use the word equal because equal means, in geometry, exactly the same, as in same location. So when we use the word congruent, we mean they're the same length or the same size or the same shape, depending on which figure we're talking about, but probably in a different location. Okay, so two congruent segments are segments that have the same length. Now there's some different notations, so make sure you've got this in here correctly. This notation is for congruent. It's got two equals, like two lines for equal signs, and it's got sort of that tilde on top of it. But we only use the value equals, or the symbol equals, and they have the same size, shape, and location. Okay, so we would never say one segment equals another one unless they're exactly the same segment. But we can say that they're congruent, meaning they're the same length long. Two segments that are marked with the same number of hash marks are understood to be the same length. So these two shapes right here, we would say are the same length because they both have one blue hash mark on them. And you'll usually see this happen inside of another geometric figure. So like maybe you have a triangle and they mark two sides with a hash mark. Now you know these two sides of the triangle are equal in length. That's where you see it happen a lot. Now, because these two are equal in length, we say that they are congruent. And if we were to want to write that down, we would write down then that AB, remember it's a segment, we talked about that last time, so you put the segment topper on it, is congruent to the tilde and the equals, segment CD, again with a line on the top of it. Now there is one other thing that we could write down about this pair of segments. Let me write it and then I'll read it. Why is that true? What does that say?
The length of AB is equal to the length of CD, but it doesn't have the segment bar on top that says that it's CD.
Right. So the segment bars on top tell you you're dealing with a segment. When we leave the segment bar off, we're talking about the length of it. So Amy read it exactly right. When you see the AB without the line on the top, it's saying the length of AB. And on the right-hand side, it's saying the length of CD. So then it becomes appropriate to put an equals between, because this means this is a numerical value. They're lengths. They're numbers. So is it appropriate to say one number equals another number? Well, of course. We do that in math all the time. 5 equals 5. No problem. So that's what this statement is saying. This one's saying that two numbers are the same, not two segments, right? The first one is about segments being congruent. The second one is about lengths of segments or numbers being equal.
And shape, correct?
Yes, but for lines don't have shape because they're only they're really only a one-dimensional object, so they don't actually have shape to them. We will have more of an issue with the shape when we get to two-dimensional objects like triangles and squares and stuff like that. Yeah. All right, we can have congruent angles as well. So if congruent segments are segments that have the same length, then congruent angles are angles that have the same measure. We call it measure. Again, we see that same congruent symbol that we saw earlier, right? Same one. To indicate that two angles are congruent. So in our diagram here, you see some things marked. So we're going to write these down in a minute. But what I want you to notice here is that there is another equal sign here, right? So why is there an equal sign? Well, there's an equal sign because when you put the M in front of it, it means measure of the angle. So again, this statement is a statement about numbers. It's about the angle's measures being equal. Not the angles themselves, but their measure. So we can put equals between those. But we could also write angle DAE is congruent to angle EAB. And we put the congruent sign between those two, because that's actually talking about the angles themselves. Okay, so let's look at the angles themselves. If you look at DAE in the diagram and EAB in the diagram, we are on the right-hand side over here, and we know that they are congruent, or that their measures are equal, because they both have two hash marks on them. That's why we know, or at least how we're being told from the diagram. Two angles marked with the same number of arcs, or whose arcs have the same number of hash marks, are understood to be congruent. Your book does it like this. They like to put like a hash mark on one, so you see that on the right-hand side over here, one hash mark on each of those, and on the left-hand side they have double hash marks. Some books that you will see, let me just draw another angle for us that we can reference. What they will do is they will just mark like this, and that would be equal because they're marked both of them one time, or if they marked them both twice, that would be congruent angles or equal measures, so they'll do it like that. So it's one of the two. It just depends on there's not a always it's done this way kind of thing. Both of those are options. Okay, still got 5 minutes, right? Regular polygons. Regular polygons are polygons that have two features. So let me talk about the two features individually first. The first feature is equiangular. Equiangular means it's a convex polygon with all of the inside angles, the interior angles congruent. Equilateral means that it's a convex polygon with all of its sides congruent. And if it is both equiangular and equilateral, then it's regular. And these are pictures of regular polygons on your paper right here, or on my slide right here. What's the first one's shape? Pentagon. And what's the second one? It's a hexagon. Okay? We know that they are regular because they've got all of the congruent pictures. See, I actually put one in here. I did, right? This one right here, this picture, has all of the angles marked with the doubles. You guys see that? Okay. Okay, so they've got all the angles marked as being congruent. They've got all the side lengths marked as being congruent. Therefore, the shape is both equiangular and equilateral, and therefore it makes it regular. So, the last thing we're going to do is examples 1 and 2. What I want you to draw on examples 1 and 2, without looking at each other's papers, and if you can't think of one, I promise we'll all write one down, okay? So this is not like a test, okay? Just see if you can think of a way to draw a polygon that's equiangular and not equilateral. That's the first one. And the second one that's equilateral and not equiangular. Okay? See if you can draw one. So it doesn't have to be a pentagon or a hexagon. You can make it a triangle or a square, rectangle, quadrilateral. I mean, whatever shape comes to your mind, see if you can play with that shape and make it one of the things and not the other. Okay? So I'm going to give you 2 minutes to try. And then I want you to share it with a neighbor and see what you can come up with. And then I'll give you a couple of them, or I'll let you guys give me a couple of them out loud. Okay, share whatever it is you have at the moment with somebody next to you, or a couple people next to you, whatever kind of works out. Just look at what they have, look at what you have, see if it works, see what you think. All right, I'm hearing some questions about triangles, so let me answer a general question about triangles right now. Triangles can't be used because automatically equiangular and equilateral. If you've got one, you've got the other on a triangle. So you have to have something at least 4 sides. And 4 sides is enough to get the picture in either place. So I'll draw you an example of the simplest ones, I think, in both of the cases, and then we can see what else you guys maybe came up with. The simplest thing for number 1 is actually a rectangle. That's your simplest, okay? A rectangle, make it a little bit thicker, is equiangular, correct? Four congruent angles are all 90 degrees, but we have sides that are not all the same. At least they don't have to be. Okay, that's the simplest. The second one, a polygon that is equilateral but not equiangular. The simplest one is a rhombus. And I know we haven't specifically talked about rhombuses in here, although I suspect that you have seen and heard about them before. You do need to make sure that it's a rhombus that's not a square, or that's not going to work. But you know, what you're wanting to imagine is kind of the basic shape of a kite, or a diamond. That's what my daughter would have called it. It was a diamond, probably, right? And my diagram's not perfect because it doesn't really give the illusion that they're all the same, but pretend for the moment that they are. Yours, I'm sure, is much better. What else did you guys have for the first one? Equiangular and not equilateral. Did we draw anything differently? That's what you had?
Why did you say triangle wouldn't work?
It automatically forces it because there's only the 3 sides. So you can do this with 4 sides because you can manipulate 2 sides at once. The first one on here, imagine a stop sign that you pull out. That's kind of what happens to a rectangle, right? It's a square that's been sort of oblong, you know, I don't think this is a word, but made more oblong. Oblongated, that's definitely not a word. Okay, but take it, huh? Elongated, that's the word I want. Thank you so much. Elongated, yes, thank you. So if you take I was saying a stop sign, octagon, thank you. An octagon, and you elongate it, it would still have the same features as the first one, right? And then the second one, making a polygon that's equilateral but not equiangular, you can do it really easily with another shape too. Did anybody do something different than a rhombus? What did you have, Alyssa?
Like a house shape.
Yes.
I don't know.
It's exactly what I would suggest. How many sides does it have? 5, which makes it a pentagon. Yeah, so a pentagon also works really nice. So this is the basic shape that Alyssa's referring to, and that's another one that's really, again, it does not give the illusion that they're all the same, but Bézier's probably does, so mine doesn't. But pretend for a moment. They're all the same now. Okay, house length. All right, we will pause here today on this.